If you've ever held a golf ball in your hand and actually stopped to look at it, you've probably wondered why it's covered in hundreds of tiny dents. It looks deliberate, almost obsessive, like someone went out of their way to make it imperfect. And that's the hook, because in physics, engineering and flight, perfection is often the worst option. Today, we're going to break down one of the most misunderstood design choices in sports, and by the end of this video, you'll never look at a golf ball the same way again. If this is the kind of deep, no-nonsense explanation you enjoy, this is one of those channels that rewards sticking around. So make sure you don't miss what's coming next by joining the community here. The smooth golf ball era nearly crippled the sport before it even matured. In the earliest days of golf, balls were smooth. Completely smooth. Craftsmen worked hard to make them round and polished, believing that a perfect sphere would cut cleanly through the air. On paper, that makes sense. In reality, it was a disaster. Smooth golf balls flew low, dropped quickly, and behaved unpredictably once they left the club face. Players had to hit harder to achieve distance. Accuracy was inconsistent, and long shots were limited by physics no one yet understood. Golf was being constrained not by skill, but by aerodynamics. Then something interesting started happening. Players noticed that their older balls, the ones that were scuffed, dented and beaten up from repeated play, travelled farther than brand new ones. These balls weren't prettier, they weren't rounder, but they flew better. At first this was chalked up to superstition or coincidence. Eventually it became impossible to ignore. The damaged balls consistently outperformed the smooth ones, and that observation quietly set the stage for one of the most important aerodynamic discoveries in everyday life. Golfers accidentally discovered drag reduction long before they understood it. Once players realized rough balls flew farther, they started taking matters into their own hands. New balls were intentionally scratched, nicked and roughened. No one knew why it worked, only that it did. This was pure trial and error, but it exposed a core truth about how objects move through air. Smooth surfaces don't always behave the way intuition suggests. Air doesn't slide cleanly over them. Instead, it separates too early, creating massive drag that slows the object down. This is where two critical ideas enter the conversation: drag and lift. Drag is the force that resists motion through air. Lift is what allows an object to stay airborne longer. Early golfers didn't have those words, but they were witnessing both effects firsthand. Their roughened balls experienced less drag and stayed in the air longer. The question became how to recreate that effect consistently without destroying the ball. Dimples work because they control the air, not because they reduce friction. The real breakthrough came when engineers and physicists studied airflow around a golf ball. When a smooth ball moves through air, the air sticks briefly to the surface, then peels away abruptly, forming a large, low-pressure wake behind it. That wake acts like an invisible anchor, pulling the ball backward and robbing it of distance. Dimples changed this completely. Each dimple trips the airflow into a thin layer of controlled turbulence called the boundary layer. Turbulent air sounds bad, but here it's exactly what you want. This turbulent layer clings to the surface of the ball longer before separating, dramatically shrinking the wake behind it. Smaller wake means less pressure drag. Less drag means more speed retained through flight. This is the part most people get wrong. Dimples don't make the ball slippery. They make the air behave differently. A dimpled ball actually experiences more skin friction but far less pressure drag, and the net result is a massive performance gain. A well-struck dimpled golf ball can travel more than twice the distance of a smooth one under identical conditions. Dimples also unlock lift by amplifying spin through the Magnus effect. Distance alone isn't the whole story. Golf balls don't just move forward, they spin. When a ball spins backward through the air, it changes how air flows above and below it. This creates a pressure difference that generates lift, known as the Magnus effect. Dimples amplify this effect by stabilizing the airflow around the spinning ball. Without dimples, airflow separates too early for spin-induced lift to fully develop. With dimples, the airflow stays attached longer, allowing backspin to produce meaningful lift. That lift counteracts gravity just enough to keep the ball airborne longer, flattening its descent and extending carry distance. This is why modern golf shots arc smoothly instead of dropping like stones. Modern golf balls are aerodynamic engineering projects hiding in plain sight. Today's dimple designs are anything but random. Manufacturers experiment with hundreds of variables, including dimple count, depth, shape, edge sharpness, and layout. Most balls fall between 300 and 500 dimples, but the exact number matters less than how they interact as a system. Some dimples are shallow for high-speed stability, while others are deeper to maintain lift at lower speeds near the end of flight. Wind tunnels and computational fluid dynamics simulations are used to test these designs under real-world conditions. Engineers tweak patterns to optimize distance, control, spin rate, and consistency. The goal isn't just maximum distance, but predictable flight across a range of swing speeds. What looks like a simple white ball is actually the result of decades of aerodynamic refinement. The dimpled golf ball proves imperfection can outperform perfection. The lesson hidden inside a golf ball is bigger than the sport itself. A perfectly smooth object feels ideal, but physics doesn't reward aesthetic perfection. Controlled disruption often produces better outcomes. This same principle appears in aircraft wing textures, race car surfaces, and even energy-efficient vehicle design. The golf ball just happens to be the most familiar example. As technology advances, designs may continue to evolve within regulatory limits, but the core principle will remain unchanged. Dimples aren't a gimmick. They are a precise solution to a complex problem, discovered accidentally and perfected scientifically. If you learn something new today, pass it along to someone who would appreciate the explanation, and make sure you stay connected here for more deep dives into the hidden mechanics behind everyday things.